Welcome to example number 11 called Anyone Can Be a Ballerina. So a student stands on a rotating platform, which is shown here. We'll assume that there's no friction on the platform, but it's able to rotate with ease. And he's holding two 5-kilogram dumbbells on each of his arms, 1 meter away from the central axis here. Another student comes along and gives him a push and starts the system of the student, the dumbbell, and the platform rotating around at 1 revolution for every 2 seconds. The student on the platform then pulls the dumbbells towards his chest so that it reduces his rotational inertia and his angular velocity changes. Hopefully you'll realize that he'll actually spin a lot faster because he'll have a smaller rotational inertia. And the key in this problem is conservation of angular momentum. So we're assuming momentum angularly is conserved. If you look earlier in our notes, you'll see a section on angular momentum, which we define as L, is the symbol that we use for angular momentum, is equal to the rotational inertia I multiplied by the angular speed or velocity in radians per second. The angular momentum is conserved, where delta L will be 0 if the net torque on the system as a whole is 0. And it is. So basically that net torque is 0, so therefore the change in angular momentum is 0, meaning the final momentum minus the initial momentum is 0, so we could say that the momentum initially and the momentum finally are equal to each other, as shown down over here. So returning back to our problem, if you want to find the new rate of rotation, we're going to need to use conservation of angular momentum. So part A, the key will be angular momentum initially equals angular momentum finally. And angular momentum is rotational inertia I multiplied by angular velocity omega. So we have I initial and omega initial equals I final times omega final. So what is the moment of inertia initially, and what is the moment of inertia finally? And what is the angular velocity initially, and what is the angular velocity? Well, that's what we're trying to find in part A. So the rotational inertia I, we're told that the student, when he has the dumbbell, his arms outstretched, he has a rotational inertia of 3 kilograms times meters squared, but he also has the two dumbbells. So how do we include that into the problem? I assume that this number here includes his whole body, his arms and his legs and everything. And really we just need to include what is this bit and this bit in the problem. They both have mass m and they're a distance of, let's say, r away. Oh, and I have two of them. And if you recall, the rotational inertia for any object that has mass m, a distance r away, is just mr squared. So it's mr squared. M times r initial squared. So in this problem it would be 3 plus a mass of 5 kilograms multiplied by a distance of, where is that distance? Oh, 1 meter from the axis, so 1. Oh, and remember that there are two of them, so we really need to multiply this by 2 over here. So we have a 2 here, put a 2 over here, and by the way, this is squared. So his initial moment of inertia is going to be 13 kilograms times meter squared. Okay, what about afterwards, when he brings those arms in? Whoops. So let's look at I final. I final would be very similar calculation. When he brings his arms back towards his chest over here, as shown in the picture, his rotational inertia is said to be dropped down to 2.2. So that's 2.2 kilograms times meter squared. That's the rotational inertia of his body. And then we have the masses that are located not as far. So they have mass m, but they're now at a different r. We'll call that r final. Maybe this was r initial over here. So we have two of them, 2 mass, but then r final squared. So that's going to be 2.2 plus 2 times the mass is still 5 kilograms each, multiplied by the distance. Now they're only 0.2 meters away from his central axis, so 0.2 squared. So then his rotational inertia will drop down to 2.6 kilograms times meter squared. So we now know the initial moment of inertia, the final moment of inertia. Do we know the initial angular velocity, omega? Well, we're told that he makes 1 revolution in 2 seconds. So that's basically 1 revolution divided by 2 seconds. But remember, we need to keep our, well, I guess we could leave it in revolutions per second. If we wanted to, we could put it in rads per second. But now that I look at my answer over here, and it's okay, I didn't specify whether radians per second. So let's just leave this in revolutions per second. So then that means omega final will be in revolutions per second. So let's substitute in here. We have 13, then multiplied by 1 over 2, which is basically 0.5, equals 2.6 times omega final. And then solving for omega final, we get 2.5 revolutions per second. That's part A. In part B, we're asked to calculate the initial and final kinetic energies. Now, he's not moving anywhere translating-wise, but he is actually rotating. So he does have a difference in rotational kinetic energies. So rotational kinetic energy is 1/2 I omega squared. So if we're doing it for the initial point, we're going to do 1/2 times I initial times omega initial. So it's going to be 1/2 times 13 times, now we do want this kinetic energy to be in joules, preferably. So we do need to convert this omega to actually in radians. So 1 rev per second for 1/2, I guess, revolution per second. We're going to need to change revolutions to radians. So remember, 1 revolution, if you go around an entire circle, you go 2 pi rads, or radians. So we're going to need to multiply by 2 pi in here. And this is being squared. And I get an answer of 64.15 joules. I'll just write this as 64 joules. Okay, let's now find the final kinetic energy of the system, 1/2 I final times omega final squared. So that's 1/2 times his final rotational inertia, which is 2.6. His rotational speed is 2.5 revolutions per second, which we have to convert to radians per second. So that's 2 pi rads per 1 revolution. The revolutions cancel out, and we get rads per second, and that's all being squared. And this gets us an answer of 320.76. So it's actually 321 if we're going to go 3 sig figs. So 321 joules. So wow, the rotational kinetic energy increased. There was not a conservation of kinetic energy. So how did suddenly his kinetic energy increase? Where did that energy come from? And that's what is asked in part C. So this extra kinetic energy came from the fact that the student had to do work in moving the masses closer to his chest, from the initial picture to the final picture. So work was done by his arms in moving the dumbbells towards his chest. And in fact, this work is equal to the change in kinetic energy. You see, a lot of people might be tempted to say that the kinetic energy is the same without doing any calculations, and it isn't. It's really not an isolated system. So the student had to do work in order to move the masses closer to the center of rotation, and this extra kinetic energy came from the chemical potential energy stored in the body of the student. And that's it for example number 11.